Oh, by the way, let me. All right. So no question. By the way, are you guys going through all of these topics by your own self as well after the class, or um, I mean, I would suggest that you should go through what we covered during the class using your books and so on. You can also find all these notes on the website of Mega Lecture, and under the notes section there would be physics notes by Basil, and you can find all these notes in there as well. Okay, so I'll assume that no one has any question at the moment, so
Sir,
we'll
electric field formula, we have to learn this, or will it come in the formula sheet?
which these formulas that you see over here.
Yes.
Oh, some of these are given in the formula sheet as well, right? So you can check which ones are really given in the formula sheet and the ones that are not. It's easier to really derive these expressions, and you can really do that if you understand the physics behind these expressions. It's easier to derive all of them. Maybe you might be given one of the expressions, and so for example, let's suppose that you are given electric field but not the potential difference. But if you know what what relates electric field and potential difference and how the physics behind it, then you can write down the expression for the potential difference as well in terms of field expression, right? So it's really just potential difference is electric field times distance, right? It's something like this. So the distance is really the distance between the two plates where the electric field exists between those two plates. Anyways, that's we'll discuss that in more detail in electromagnetism. So this whole thing at this point that you see over here, it's just how the equations of electromagnetism are really related to the equations of gravitational fields or gravity. But even though there is all this resemblance in the equations, it is a problem in unifying electromagnetism with gravity. It's still a problem. You can do that if you consider an extra spatial dimension and then you work out. But that's not the scope of this course. But that's something that that was done by Kaluza and Klein, and they. Anyways, we are going ahead of ourselves. But anyways, so any other question? And does that answer your question, by the way? Okay, so no more questions. All right. So last time we discussed gravitational potential and how can we write down the gravitational potential energy using the gravitational potential. And so we'll continue from there, and we'll just these are just how electricity and gravity are kind of very familiar. There is some analog relation between the two. So in electric field, where you have a charge, in gravity, the analogous of the charge is really a mass, and in electricity you have a field. You still have this concept of field, but that field is electric field in electricity, while in gravity you have gravitational field. In of course, in electricity and magnetism, you also have another type of field, which is the magnetic field. And so there are, but in reality, those two fields are the same thing: electric field and magnetic field. They are like two sides of the same coin, basically. So, and then these are some of the expressions how forces are also, the expressions for forces are very similar, and they both follow the inverse square law and all of that, right? So this is just seeing the resemblance between electricity and gravity. So anything that you would like to add to this, or ask a question, anything that is bothering at this point? All right. Okay. So then we'll continue and we'll discuss what is called orbital mechanics, really. Now, uh, consider that you have an Earth satellite system. So here is the Earth, and let's just very poorly draw a satellite. And here is a satellite, and it orbits the Earth like this, right? The velocity of this satellite would be the linear velocity of the satellite. The vector points like this, and the weight of the satellite, where would that vector point? By the way, the weight, this is the velocity vector, the linear velocity. Where do you expect the weight vector to be pointing? Anyone? This dotted line is the orbital trajectory, or the path that the satellite takes around the Earth. This is the Earth. Let's say it has a mass m. So the weight would be towards the center of the mass m, right? Towards the center of the Earth. So that's where this vector would point, mg, right? Now, if I want to write down the total energy of this satellite, what would be the total energy of the satellite? It would be its potential energy, because it is away from the surface of the Earth. So it would have some potential energy, but it's also orbiting the Earth, and it will carry some linear velocity as well. So it would also have some kinetic energy. Right. So you can also talk in terms of forces. What force would be providing the centripetal force to this satellite? It would be the force of gravity, right? The force of gravity is providing the centripetal force, which the centripetal force is really the one that is going to keep this satellite in circular path around the Earth, right? So that is gm m by r squared. This is the gravity, and the resultant of this gravitational force is what is that the satellite is in the orbit of the Earth. So that's mv squared over r. So the gravity is providing it the necessary centripetal force. Right. So from this, then you can work out the equation for the velocity. Now, what velocity is that, by the way? If I work out an expression for this velocity, what velocity is that really? Anyone? No, no. You can answer even if it's wrong. It doesn't really matter.
Angular?
No, it would not be an angular velocity. This is, let's say this is the linear velocity, right? So this velocity is linear. What would be the nature of this velocity? Think about this, that this, what are we doing? We are equating the force of gravity with the centripetal force. And that really means that the gravity is providing it the centripetal force. At the moment, you're right, we can write it in terms of the angular velocity as well, and we can work out an expression for the angular velocity. So that's completely correct. But at this point, this velocity really is that linear velocity that this satellite carries when it is in the orbit of the Earth. And so you can also, what you can do is you can also compute what is known as the escape velocity. And by the name of escape velocity, it's really clear that an escape velocity is the velocity that this satellite would need to overcome the gravity of the Earth. And so it would really escape the surface of the Earth, right? Now, how can I figure that velocity out? I need to think in terms of the kinetic and potential energy. So when my potential energy, when the kinetic energy is exactly equal to the gravitational potential that is being produced by this Earth, at that point, I can say that that is the minimum velocity that I need from this expression to escape, or you can say that is the minimum kinetic energy I need to escape this potential. So what I mean is that the potential is minus G M M by R, right? And the kinetic energy is plus, it would be half mv squared. Now, these are the initial energies, and the final energies are 0, because it's not going to be moving, and there is no more. It will not be in the field of the Earth. The satellite will not be in the field of the Earth. So that's why the potential energy is 0 as well. So what I can do from this is I can work out the velocity. And the reason I'm doing this, you could have also written this same expression as the kinetic energy equals the gravitational potential energy, like this. What this physically means is that if I need to escape this gravitational potential, my kinetic energy should be at least equal to this potential. So kinetic energy is really the energy that you need to get out of this potential, Gm by R. So this is then, if I work out the velocity from this expression, which is 2Gm by R square root. So I'll just write it as power 1 by 2, or let's just write it as a square root. So no confusions. This is that velocity which you need at minimum to escape the gravitational pull of the Earth. So is that clear? Is the
Yes.
idea of escape velocity clear?
Yes.
Yes, sir.
Okay, perfect. So now let's come back to this this expression where we will be indeed working out the angular velocity. So we know that where can I do this? Let's do it over here perhaps. or let's do it over here. Okay, so we know that G m by r squared is the force that is providing the necessary centripetal force to the satellite to keep it in orbit, which is mv squared by r. We also know that we can relate the linear velocity with the angular velocity with a factor of r. So if I use this in this expression, this thing becomes mr omega. And on the left hand side, we have gmm by r squared. And you can use this expression now to write down the angular speed with which the satellite orbits the Earth as, so m goes like this, and you're left with, well, this would be omega squared, right? So omega squared is g m by r cube. So is that okay? Do you understand how did I write this as mr omega squared?
Sir, what
Because,
does omega mean?
oh, it's the angular velocity of the satellite, which means that it is that particular velocity which, or you can say it's the rotational velocity with which the satellite rotates around the Earth, which really means it is orbiting the Earth with this velocity, angular velocity, omega. So does that answer your question?
Sir, does omega like derive into something else further? Like, do we have a separate formula for omega?
Oh, you mean, yeah, so first let me just quickly write this down, and then I'll, so this is gm by r cube. We just took the square root. Okay, so now what you're asking is that, yes, we have, right? And you have seen that as well in the circular motion. Omega was written as really 2 pi by the time period. And that really comes from the fact that if something is moving in a circle, it starts from its journey from point A. So let's take that this is a vector and it starts its journey from point A. This vector is pointing from the center to this point A, and it moves in this direction and it comes back to point A, right? So it's moving like this, it will move, and it will come back to point A. So really it has covered an angular displacement, which is theta, which is 2 pi, right? Because it has really covered an angle of 360 degrees, which is in radians is just 2 pi. And we'll divide this thing by the time period, which is the time that it takes to complete this one revolution. So that is your omega as well, right? So that's the another expression we have for omega. But this one is really a general expression in terms of a circle. And you can use this expression for omega and relate it to this one to find the time period as well. And that's Kepler's third law as well, right? It's the relation for time period to angular velocity. So exactly, so that's what we'll be doing this now to find out the time period of the satellite. So what would be the time period for, how much time does the satellite takes to complete the one revolution around the Earth? So that's clear, right? So that's okay?
Yes, sir.
Okay. It's okay for everyone, right? Omar, you asked me this question, by the way.
So I didn't ask.
Oh, I think it was Hasib. Sorry. Okay, right. So yeah, so it's clear now to you as well?
Yes, sir.
Okay, perfect. So So now you did the problem mainly for us, you solved it for us, because we'd be really relating these two expressions for omega. And so that's 2 pi by t is equal to square root gm by r cube. And this really gives you the expression for time period, right? So I just have to rearrange this. Okay, so I think okay, we'll talk about that after some time. But so if I just rearrange this thing, we have time period as, so we have 2 pi, and we bring t over there, and we take this over here. So we really have 2 pi square root r cube by gm is equal to t. And from this, you can write that t squared, if you squared both the sides, then you can say 4 pi squared r cube over gm. That's your t squared. And this gives you the Kepler's third law, which is t squared is proportional to the cube of the radius. So is that clear? How we can write down the time period?
Yes.
Okay, and the understanding of time period is clear as well? What it means, or what the time period really physically means? So it's really just
Yes.
the time, yeah, so it's really just the time that the satellite takes to complete its revolution or an orbit around the Earth. Okay, so if you have the time period, you can also work out the frequency. It's just frequency of the this motion would be 1 over the time period, and then you can do the math yourself, right? Just put the value of time period in here, and you can do that. All right. So
Sir, what does a
yeah.
frequency do here in this field?
Oh, frequency is just really telling you how fast this orbital motion is happening. So the higher the frequency, it really means that the faster the orbit is being completed, right?
Yes.
So anything that has a higher frequency, it means it really is telling you about the speed of that oscillation. So the higher the frequency, the faster the satellite completes the orbit. All right, so let me just check how much time do we have. Okay, we have around 9
Sir,
minutes.
can you start physics class 10 minutes late because we have chemistry as well before this?
Oh, right. Okay. So you have which chemistry? A2 chemistry?
Yes.
Okay, A2 chemistry. Right. So just text me, drop me a text, or maybe message this in the group as well. It will just remind me, so I'll check with the timetable, right? Is it, by the way, now that you have touched upon the topic, we have really made a proper timetable. And what the other thing was happening is that I'm also taking NET physics classes as well, but they are they have now stopped because NET is just happening now from the 1st of July. So I might have that slot free, which is 4 to 5. So does that work for you guys? Just asking. I'm not confirming the time. I'm just saying if that works for you guys. Just asking.
Yes, sir. Well,
So you don't have none of you have any class at that time, right? 4 to 5.
So 4 to 5 Pakistan ka time, right?
Yeah, 4 to 5 Pakistan time. Yes.
Oh.
PST time. So no problem for anyone.
No. No, sir.
All right, great. So we'll check. I'll check with that. We might change it to 4 to 5, or if that doesn't work out, we'll start the class 10 minutes late. Both works for me, although I'd prefer shifting the class to 4 to 5 as The night time is really very tiring for me. Anyways, so is there any question from whatever we have done so far? Quickly, anything that you have to ask, anything that you did not understand, or anything for that matter? Okay, so I'll assume that there is no question at this point. Okay, so we'll move to this next topic, which is of geostationary orbits. Any idea what is a geostationary orbit? Anything that you might think of a geostationary orbit?
An object that revolves around the Earth.
Yeah, it revolves around the Earth, but we're specifically talking about geostationary object or the orbit, and so it's really an orbit where the time period of this object, which is revolving around the Earth, is 24 hours, which is exactly equal to what? The time period of the Earth, right? So it's it's the time period of the Earth when Earth rotates. It completes its orbit revolution or rotates in 24 hours. So that's 1 day basically for us. So imagine something like this, that you have this Earth and a satellite is orbiting this Earth. Okay, so putting my drawing skills to the test. Let's just see what does this do. Okay, so here consider that this is the orbit, right? So it's moving like this. So you're really imagining a satellite which is orbiting this Earth, and its orbital path is directly above the equator, right? So that's the equator, and the orbital path of this satellite is directly above this equator. So it aligns with this thing, right? Is this thing, and it's directly aligning with the line of this equator. Now, if the satellite, the Earth is also spinning. So let's suppose that the spinning of the Earth is, well, the spinning of the Earth is really like this. So what I have drawn over here is that the satellite is orbiting the other way. So let's just change that for a minute, and let's say that this would be, it would be orbiting in this direction. So like this, right? So in the direction of the rotation of the Earth. Now, if that happens, which means that the orbit of the satellite is in the same direction as the rotation of the Earth, then you would have a time period of 24 hours. And this, it will remain over the same point above the Earth's surface, the satellite, right? And so to an observer who stands on the Earth, the satellite will appear as though it's stationary over there, as if it's not moving. Why? Because the observer who is standing, I'll just use this thing here only. So the observer who's standing on the Earth, he is rotating as well with the Earth, with the rotational speed of the Earth, right? So this is the rotation of Earth. And if you're standing on the Earth, then you are as well rotating with the Earth. Now, if the satellite as well is in the same, in this orbit, and it's rotating with the Earth in the same direction as the rotation of the Earth, then what happens is that the satellite appears as though it's stationary. So you have to think in terms of relative motion, really. So are you getting this point, or did I just confuse you?
Got it.
Okay, so you're getting it. Okay, good. So now the time period of this thing would remain same. This radius of orbit will also remain same. So it could be any radius. You'd have a fixed value for that, and the angular speed would also be fixed. So you would be the satellite would be rotating around the Earth with the angular speed of the rotational speed of the Earth. So these things would remain same. But when you send a satellite, it could have different values for mass. So this is not going to be same every time, which is why there would be different values for the kinetic energy, the gravitational potential energy, and the centripetal force, right? Because all of these things involves the mass.
Sir, how
So
is
for
R
different,
going to be the same?
yeah. Oh, because it's going to orbit the Earth at that sweet spot where you're allowed to orbit the Earth. If the R increases from that, then the satellite goes out of the orbit and it flies away really in that direction. If R decreases, then it again moves closer from its closer towards the Earth and moves away from that sweet spot really in which it was orbiting, and it would really